All right, so welcome everyone. My name is Marcel de Carli Silva, and I'll be the chair for this plenary talk. We're very grateful for having Luca give this talk here. I don't think Luca needs any introduction. I'll just say that he's held faculty positions at Columbia, Berkeley, and Stanford, and recently he has gone back to Italy. So Luca will talk about graph and hypergraph sparsification. And well, Luca, please get started whenever you're ready.
Thank you for your introduction. Thanks to the organizers for inviting me. And I would like to use this opportunity to tell you about some recent work by me and others on the problem of approximating dense graphs by sparse graphs. So that's in general a kind of fairly broad goal that in part depends on what we mean by approximation. For example, if we want to find, given a dense graph, a sparse one where distances between vertices are roughly the same, that's the problem of constructing spanners, which is not the one that I will talk about. Instead, what I'm going to be interested in telling you about today, it's when given dense graph, I want to construct a sparse one over the same set of vertices with edges that are possibly weighted in such a way that the cut structure of the graph is approximated. Meaning that if I look at any subset of vertices in the original graph, and then the corresponding set of vertices in the new graph, the number of edges that are cut, meaning at one endpoint in the set, one endpoint outside the set in the original graph, it's roughly the same as the number of cut edges in the sparse graph when you count also their weights. So the weighted number of cut edges is roughly the same. So that means that if the sparse approximation is good in this sense, that every problem that relies on the cut structure of the graph, like problem of finding ST cut in the graph, or a global min cut, or a max cut, or a good clustering, well, all those problems have approximately the same solutions in both graphs. So it might be more advantageous to solve those problems on the sparse approximation, because having fewer edges means also that it will take less memory and less time to work on the sparse graph. So this concept was introduced by Ben-Zur and Karger. They said they were interested in getting an epsilon approximation in the sparse graph. So they wanted all possible cuts to be off at most by a multiplicative factor of 1 plus or minus epsilon. And the pipeline that I had in mind in giving this definition was that once we're able to construct a graph like this, then if we have any problem like a max flow problem or min cut, max cut, clustering, as I said before, we can apply those algorithms not to the original graph, but to the sparse approximation, and then get still a good solution to the original problem, but work with a smaller graph, and so have faster running time and less memory use. And later, Spima and Tang introduced a stronger notion of approximation. So one that is harder to achieve, but also is more useful in application. So according to Spima and Tang, a sparse graph H is an epsilon good approximation of a graph G. Is the following condition that seems a bit strange is true. So let's walk through this. So in this condition, we are going to look at all possible ways of assigning real number labels to the vertices. So all possible vectors indexed by vertices, which means we can assign a real number to every vertex. Then for every such way of assigning real numbers to vertices, we want the sum of difference squared along edges, possibly weighted by the weight of the edge, to be roughly the same for the two graphs. So the way it relates to the Ben-Zur-Karger definition is that if instead of looking at all possible real value labelings of the vertices, you just look at 0, 1 labelings, first of all, this corresponds to subsets of vertices. And also, if you have a 0, 1 labeling of the vertices of a graph and you compute an expression like this. Well, think about what this expression looks like. The quadratic term will be 0 if you have an edge goes from a 0 vertex to a 0 vertex, or from a 1 vertex to a 1 vertex. And it will be 1 if you have an edge that goes from a 0 vertex to the 1 vertex. So what you're doing when you look just at 0, 1 assignments of real numbers to vertices is that you're looking at a cut, and then you're counting the weighted number of cut edges, which is precisely the Benzout-Karger definition. However, you are not limited to 0, 1 labelings. You can sort of look at arbitrary real value labelings. That's why it's a stronger definition. And it's actually a very natural definition if instead of thinking about the graphs, we think about a matrix called the Laplacian matrix that can be associated to every graph. Then graph H is a approximator of G in the Spielmann-Tank sense if the respective Laplacian matrices are close in a sense that is meaningful from the linear algebra point of view, that they are upper and lower bounded by each other up to epsilon in the positive semi-definite ordering. Now, it's precisely for linear algebraic applications that this stronger notion was useful. In particular, Spielmann and Tank were interested in solving systems of linear equations, the most basic problem in linear algebra, at least systems of linear equations of a certain form called symmetric diagonally dominated. And for each such linear system, it's possible to associate a graph to it in a kind of one-to-one way. And basically, this condition on the graphs associated to two systems of linear equations implies that they have roughly the same solutions. And sparsity of the graph corresponds to number of non-zero entries in your system of linear equations in a matrix of coefficients. So sparsifying a graph in a sense of Spielmann and Tank really means that if you have a certain type of linear system, you can transform it to another that has the same approximately set of solutions, but much fewer non-zero entries in the matrix of coefficients, so that you can have much quicker solvers through iterative methods. So the applications of sparsification are really both algorithmic, in that applying an algorithm to a sparsified object will be faster, but could also be a good notion of lossy compression for the graph, meaning that you could even in some applications throw away the original graph, only keep the sparsified graph. And since this has potentially much fewer edges, it also means that it can be stored much more cheaply. Now, for this kind of considerations, what is important in a sparsification process is that you can do it efficiently. Otherwise, if it takes a really long time to find these approximations, it negates the advantages that you would get later. And you want it to have as few edges as possible. And for this talk, I really want to focus on the question of these approximations having as few edges as possible. So more of a combinatorial information theoretic kind of questions, and leave the efficiency on the side for a moment, although that's also an extremely important consideration. So it is actually pretty much known, and I'll tell you a bit about what is upper bounds and these lower bounds, how many edges are necessary and sufficient to get a good approximation for arbitrary graphs. So in particular, the result of Batson, Spielmann, and Srivastava shows that you can get epsilon approximation in the strong sense, the one that is good even for systems of linear equations, with a graph that has only constant times n over epsilon square edges. And as we will see, the constant is also small. Furthermore, even for the weaker notion, the one that only talks about cuts, constant times n over epsilon square edges are necessary, for example, to sparsify a clique. So that's the right answer to the question, how many edges do you need to sparsify a graph? So let me tell you a bit about these upper bounds and lower bounds. Maybe starting to think about how you would find a sparse approximation of a clique. So here, a good idea, which is actually an idea that would come up even if you try to sparsify arbitrary graphs, would be to just subsample from the graph, meaning just randomly pick a subset of edges, and then sort of hope that the randomness is such that roughly the right number of edges is crossing every possible cut. And in fact, this is true. For every fixed cut, you can bound the probability that it's not well approximated, and then take a union bound over all possible cuts. However, to do that, you'll need to pick of the order of n log n edges. And that's actually necessary if you are just picking edges uniformly at random, because if you go below n log n random edges, you'll start getting isolated vertices. So the cut properties will definitely be violated, even for trivial cuts where you just say how many edges come out of one vertex. However, just for the sake of approximating a clique, you can do better by picking a random regular graph. That kind of by construction will be such that every single vertex has the right number of edges incident on it. So here, in both cases, you will have to give a weight to every edge so that the total weight of the edges that you've got is equal to the total number of edges that you had before. So say that you pick a random regular graph, then all the single vertices will be the same. And with somewhat harder work than in a case in which you would pick the edges uniformly at random, you can also argue that all cuts will be preserved. So what do these observations suggest for general graphs? One is that if you're okay with n log n edges, you might have to think about some process that generalizes what happens in the clique, where you just sample edges independently at random. And that if you want to get order of n edges, well, it's possible for the clique, but in a way that is not very suggestive of what you would do in general graphs. Like, what would be a graph that is to the one that you want to sparsify in the way that random regular graph is to a clique? Especially if your starting graph is irregular, it's not even completely clear what you would be doing there. So one tricky example, so to keep in mind to imagine how this sparsification algorithm will look like, it's a so-called Barbell graph. So it's a graph that's made of two cliques over disjoint n over 2 vertices, and then there is an edge in between. So what's tricky about this graph? First of all, if you pick edges uniformly at random, and you don't pick too many, almost surely this edge in the middle will not be picked. And that gives you sort of infinite relative error, because this cut is going to be crossed by 0 edges instead of being cut by 1 edge. So the ratio is infinite. Another thing that, if you want to still do some kind of probabilistic construction, you have to pick different edges with different probabilities. Like that edge in between needs to be picked with probability 1. The other is that when you weigh the edges, you have to give different edges different weight. That's because that edge that you must pick in between must have weight roughly 1, which is the same as it had in the original graph. But then if you want to sparsify those cliques, you have to give the edges from the cliques a big weight. Otherwise, they will not add up to the same weighted number of edges. Okay, so those are two things that will have to be in any randomized construction. Different edges will have different probabilities. Also, different edges, if they're chosen to be in the graph, will have to have different weights. And that pretty much tells us enough. Like, this is all that is going on in Benzur and Karger in a sense. So their approach got, this is the paper in which they defined this concept and presented the construction. Their construction used of the order of n log n edges. And the way they approached their solution was to find, in a clever way, a way to assign different probabilities to different edges. The probability roughly had to do with how small could be cuts that include that edge. And then they sampled edges according to these different probabilities, and then weighed they weighted each edge inversely proportionally to the probability that it's being picked. So that means that every edge, if you think about having weight 0 if it's not chosen, every edge on average has weight 1, so the same weight that it had in the original graph. So every cut on average has the right number of cut edges. So it's all a matter of bounding the variance and sort of figuring out whether it's possible for some cut to deviate a lot from this average. So these were the ideas of Benzor and Karger. And Spielmann and Srivastava were able to do, for the stronger definition of Spielmann and Tang, the one with the arbitrary quadratic forms, to do sort of the same conceptual construction. Associate the probability to every edge in a different and also rather clever way, and then pick edges according to this probability, and then weighing them also according to the probability. And there is a result called the matrix Chernoff bound. So these are very useful results that tell us what happens when you pick random matrices according to certain distributions, which they use to argue that their construction worked with high probability. And even in their case, they had to use n log n edges. So something that I find a very interesting question, which I cannot state rigorously because it's sort of not clear what simple and easy to sample means. It's whether there is any way of going down from n log n to n edges with a probabilistic construction. Maybe something that would be picking a random regular graph when you're doing a click, but then would be something very different when you pick a graph like the Barbell, and so on. So it's not clear how to apply probabilistic methods to this problem below n log n. The main thing being that if you pick edges independently, you cannot do better than n log n. So you have to come up with ideas in which you're picking edges with correlations. For example, when you sparsify click with a random regular graph, regular graphs have correlations between edges. Because say, if you know that d edges incident on a vertex exist, you know that there are no more edges and so on. Batson, Spielmann, and Srivastava were able to get down to approximating a graph with order of n edges, but they did that with a deterministic iterative construction. So what they did was to choose in a very clever way the approximating graph one edge at a time deterministically, guided by a potential function. And I want to tell you sort of a reinterpretation of what happens in Batson, Spielmann, and Srivastava, which was developed by Allen, Giuliao, and Orecchio. It's actually a bit more of a restatement with a little bit of cheating, but sort of rough conceptually, that's what happens in the paper. They sort of think about this optimization problem. We're given a graph G. You want to find a graph H of best possible approximation, where there sort of is an epsilon sparsifier with epsilon as small as possible. Okay, now this problem, we know what the optimum is. It's to choose the approximation as G itself, and the error will be 0. However, you can rearrange things in such a way that this becomes a convex optimization problem that can be solved with descent type algorithms. You can set up a particular time of descent algorithm and set an instantiation of mirror descent, in which each iteration of the algorithm changes only the weight of one edge. And then you can use bounds on the convergence of these algorithms to say that if the optimum is 0, you'll get up to epsilon in no more than n over epsilon square iterations. Now, apply this descent algorithm starting from the initial solution where there are no edges at all. In n over epsilon square iterations, you get this epsilon approximation. At each iteration, you have only changed one edge or added one edge. So you have constructed your approximation with only n over epsilon square edges. So that's a very original way of thinking about optimization techniques for the sake of getting approximations. And that's roughly with a minimum of cheating what's happening in Allen Julia or Requiem. Also see how different it is to thinking about picking edges at random. It's a really very different approach. So in terms of lower bounds, Batson, Spillman, Srivastava proved that the stronger notion, the one where you could approximate quadratic forms, if you want to approximate the clique, you do need n over epsilon square edges. For the weaker notion, this was not known until much more recently. And Andoni and others had an argument where they proved that if you want to approximate a clique with an error that is about 1 over root n, you need almost all the edges, constant times n squared. And then you can adjust this argument to really get the trade-off n over epsilon squared for any epsilon. Okay, so that's what's going on with upper bounds and lower bounds for these constructions. And now what I want to tell you a bit about, it's that I want to delve into what are the constants in those big O and big omega, because there are actually pretty interesting questions in figuring that out. Okay, so these are the, let's say for the stronger notion, the one with the quadratic forms. So this is the construction of Batson, Spillman, Srivastava, the one that has n over epsilon square edges. Here I've rephrased it a little bit because this way will be neater, where I'm asking for if I want my approximation to have average degree d, so I want it to have no more than d n over 2 edges, what epsilon can I get? And so they get an epsilon which is like 2.9 over square root of d. And they show that when you want to approximate the clique, it has to be at least 1 over square root of d. So that's off only by this factor of 2.9. Now, when you so when you think about approximating a clique with graphs that are regular and where all the edges have the same weight, which is a kind of very particular type of approximation, basically what you're talking about is constructions of expanders. Expanders are bounded degree regular graphs that in many ways behave as if they were cliques. So for and in the notion of cut approximation of Spillman and Tang, that's really the notion of, it's equivalent to the notion of spectral expansion. For that, it's completely understood what is the trade-off between degree of the graph and how well it approximates a clique. There is a lower bound on the approximation, which is 2 over root d, which is the Lombo-Pana theorem from the 1980s. And there is the construction of Ramanujan graphs that say that epsilon actually can be 2 over square root of d. So then in looking at Batson, Spillman, Srivastava, it's sort of saying that you can get for arbitrary graphs the kind of approximation that Ramanujan graphs do for the clique with only this extra square root of 2 factors in the degree. And the lower bound says that if you want to approximate a clique by a graph that is not necessarily regular and that could have arbitrary weights, there is only a factor of 2 at most difference. So here I want to mention a couple of recent works by my collaborators and I. So one was to show that even for that this is sort of an improvement over this result. So it's saying that even when you allow your approximating graphs to be weighted, to be irregular, to be sort of really anything that you want, not just regular graphs, still the best trade-off to approximate a clique, it's that your error is going to be 2 over square root of the average degree instead of 1 over the square root of the average degree. So for every graph, you can do 2.9. For some graphs, you cannot do better than 2. So now we have this constant factor almost completely determined. The other is that to get the Benzur-Karger definition of approximation on a click, you can get a trade-off that is 1.6 over the square root of the degree of the approximator. So if you want to approximate in the sense of Benzur-Karger a click, you can do it better, meaning with fewer edges than what you probably need to approximate in the sense of Spielmann and Tang. So these two notions of approximation, like just preserving all cuts versus preserving all quadratic forms, there is actually a bit of a gap between them. So 2 over square root of degree compared to 1.6 over square root of degree. And here are some statements that I don't want to call conjectures because there is not enough evidence, but that I think are all plausible. So one would be that we can get rid of the square root of 2 in the Batson-Spielmann-Srivastava construction, meaning that basically clicks are the worst graphs to approximate, and that a trade-off with an error of 2 over square root of the degree is achievable for all graphs. The other is a matching lower bound, which we do not achieve for the click, we just achieve it for a certain class of graphs. And the other is that a separation between the Benzur-Karger approximation and the Spielmann-Tang approximation not only works for some graphs, but actually works for worst case graphs. That actually there is a way of separating even in the worst case. Now, in the remaining time, let me jump to a couple of variations of the problems that I've told you so far. So one is that one possible application of sparsifiers is that you might want to throw away the original graph and just keep the sparsifier, because that will still tell you, this will be a sort of lossy compression of the original graph that will still tell you about the cut structure of the graph. So a number of people have asked the question, well, but is there a better lossy compression of the graph if all you care about is the cut structure of the graph? So Andoni and others proved that no matter how you try to store a graph in such a way that you can retrieve the approximate cut structure, n over epsilon squared bits of storage are needed, and you only need n over epsilon squared log n to store a Batson-Spielmann-Srivastava sparsifier. Because it has n over epsilon squared edges, to store one edge, it takes log n bits. Interesting, Jambulapati and Sidford proved that there is a probabilistic construction of a compressed representation of a graph that uses asymptotically fewer bits, only n over epsilon. It doesn't give you the correct answer for all cuts, but it gives you the correct answer for most cuts. And so if you query this data structure, even with an adversary that doesn't know the randomness with which you created it, you're likely to get polynomially many correct answers, even though it's not able to correctly answer all cut queries. And another work that I did a couple of years ago with some collaborators was that in the setting where you want to answer all cut queries correctly, actually the right lower bound is n over epsilon squared times log n. So the Batson-Spielmann-Srivastava sparsifiers are the best possible storage that preserves the cut structure up to a constant factor. And basically our proof is to argue that if you pick a random regular graph, being able to answer approximate cut queries with an approximation which is about 1 over square root of the degree gives you a constant fraction of the entropy of the information of the original graph. A random irregular graph has d and log n bits of information, So like for every epsilon, if you replace epsilon by 1 over 10 square root of d, you'll get this n over epsilon square log n lower bound. And now the last kind of variation that I want to tell you a bit about, it's when what you want to approximate, instead of being a graph, it's a hypergraph. So hypergraph is a structure that has vertices and hyperedges, where an hyperedge, instead of being a set of 2 vertices, as in the case of a graph, can be an arbitrary subset of vertices. So hypergraphs are able to store information about a set of data items, which is higher dimensional compared to graphs. Instead of just storing relations that have to do with pairs of vertices, can be arbitrary tuples of vertices. Now, just as for graphs, you can define a notion of cuts for hypergraphs. In the case of an hypergraph, an hyperedge is cut by a subset of vertices if at least one vertex of the hyperedge is in the set and at least one vertex is not. That generalizes the case of graphs, where an edge is cut if one endpoint is in the set and one endpoint is not. So there has been some interest in defining what would it mean for a sparse weighted hypergraph to approximate a given dense hypergraph. So you would like, to, for example, to preserve all the cut structure for the definition of cut that I've just given. But there is also a linear algebraic version where there is a condition that holds for every assignment of real numbers to vertices, and that just like in the case of graphs, generalizes the notion for cuts, but has a number of additional applications. Maybe in the interest of time, we'll not say too much about this second definition, other than just pointing out that it generalizes the definition based on cuts. Again, if you take 0, 1 assignment of numbers to vertices, but it also is useful in situations where the cut definition is not sufficient. And sort of besides the motivation that led people in previous work to introduce these notions, I myself am very interested in these notions, because what's happening is that there is a lot of useful facts from linear algebra and from random matrix theory that are useful when thinking about sparsifiers of graphs. But when you work for hypergraphs, all this linear algebra is not available. And so studying sparsifications in hypergraphs is also a way to study sort of problems in graphs where you cannot use linear algebra. And it sort of forces you to think about different techniques. So for the weaker definition where you just want to preserve all cuts, there is a result of Chen, Khanna, and Nagda. I think this was in Fox 2020, so it just came out a few months ago. That is the Ben-Zur-Karger of hypergraphs. So they get the same number of edges, n or epsilon squared times log n, with a similar concept in which you sample hyperedges with probabilities that are chosen in a certain careful way. For the spectral notion, we can sort of do the equivalent of Spillman and Srivastava. So this was in a joint work with Bansal and Swanson. But we can do that only if every hyperedge has a bounded size, like say every hyperedge has at most 10 vertices or 20 vertices. Otherwise, we pay something that is like the cube of the maximum size of the hyperedges, which is a very big penalty. Although there was a previous construction that worked with n cube or epsilon squared hyperedges. So here we don't know how to get just n over epsilon squared times log n hyperedges with no dependence on the size of the upper edges. And what I consider to be the most interesting question in this area, it's whether it's possible to sparsify hypergraphs by using only constant times n, like n over epsilon squared hyperedges, similar to what Batson-Spearman and Srivastava are able to do for graphs. And there is no feasible path that I can see to extend the ideas of Batson-Spearman and Srivastava to hypergraphs, because they're so deeply rooted into linear algebra that they really don't seem to have reasonable analogs to hypergraphs. Also, we cannot hope, I think, for a deterministic polynomial time construction of hypergraph sparsifiers with constant times n hyperedges, because if we had a deterministic, provably correct polynomial time construction, some of the proof of correctness together with a transcript of the algorithm would be a certificate that what we constructed is a good approximation of the original hypergraph. But we don't expect this problem to have certificates. It shouldn't be the case, although we don't know either way, but there is a strong intuition that the fact that two graphs are good approximation of each other, we can do in polynomial time with linear algebraic techniques. But two hypergraphs being good approximations of each other, it's not something that should be certifiable. And so that's another bottleneck. So it could be that there is some way of generalizing the Batson-Spearman techniques, but in a non-algorithmic way, like finding certain analogs for tensors of what they do on matrices, but without an algorithmic component, so that we at least could prove existence of these hypergraph sparsifiers. Or we would need the randomized construction. But then even for graphs, we don't know a randomized construction. That was the first question that I asked.
Luca?
Yeah.
A question. So why, can you just say a few words about the intuition of why certifying the sparsification seems hard? What is the hard problem behind it?
Well, this is not exact. This is not the same question, but so say that I pick a random three-stat formula with some like order of n log n random clauses. That almost surely is not satisfiable, but it's believed to be hard to find any, or even they shouldn't. We don't think there even exist certificates that it's not satisfiable. However, kind of one reason for its non-satisfiability, it's a kind of pseudo-randomness properties of the hypergraph that represents which variables occur together in the clauses. And so if you were able to certify that the hypergraph in some ways a good approximation of the complete hypergraph, you could also certify that the formula is not satisfiable. So these are more analogies than rigorous derivations. But so certifying that an hypergraph kind of is like a complete hypergraph, even though it's sparse, it's so dangerously similar to certifying that a random sparse three-stat formula, say with n log n clauses, is not satisfiable. That's at least my intuition. So maybe we will have to come up with a randomized algorithm, or perhaps there is some loophole, like maybe we wouldn't be able to certify that the random hypergraph is a good approximation of the complete hypergraph, but we could construct hypergraphs together with a certificate, so that maybe for very special hypergraphs, we would be able to find those certificates. So these are all potential roads to solving this problem. So let me summarize what I've been telling you, which is that given dense graphs or hypergraphs, it's possible to find small approximations of them. Small in the sense that they have much fewer edges or hyper edges. Approximations in the sense that you preserve the cut structure and give it certain linear algebraic additional properties. How small is the number of edges? It's constant times n for graphs, constant times n log n for hypergraphs. And for graphs, there remain the question of settling what is the constant times n, which sort of relates to classical results like the Alombo-Pana theorem. For hypergraphs, there remains the issue of setting this gap between n and n log n, which I don't want to advocate it as an interesting question in itself, but as a representative question that has a linear algebraic solutions for graphs and no known technique that applies to hypergraphs. So these are the three problems that I would like to highlight. Like an analog of Alombo-Pana in Ramanujan constructions for general graphs. So what is the actually tightest, best possible number of edges in approximations of a clique or a general graph by sparse graphs, upper bounds and lower bounds. The other is whether the weaker notion of sparsification of Benzu and Karger is achievable with fewer edges than the Spielmann time construction, even for worst case graphs, so that you can sparsify all possible graphs in the Benzu-Karger definition better than you can sparsify some graphs in the spectral definition. And finally, this question, which is probably the most challenging one, which is, can you get constant times n hyperedges type sparsifiers for hypergraphs, either with a randomized construction or with a non-algorithmic existence proof, or perhaps best of all with an algorithm that is deterministic and that finds some loophole in this intuition that there are no certificates. Okay, so that's all I wanted to tell you, and thank you very much for your attention.
I'm sorry. Yeah, so thank you so much, Luca.
Thank you.
Okay, so are there any questions? If you would like to, yeah, sorry, go ahead, Marcos. Yeah.
Luca, thanks for the wonderful talk. I was wondering whether you could say a little bit about whether these constructions are parallelizable, all of them, some of them, or do you lose something when you parallelize?
Yeah, this is a very good question. The construction of Batson, Smoen, Srivastava, the one that was really kind of order of n edges, so super optimal, it's very iterative. It really chooses one edge at a time. But then there was another one by Lee and Sun, where they were motivated by efficiency, not parallelization, but they were actually choosing constant times n edges at once in a constant number of rounds. So if the way in which they choose this constant times n number of edges at each step is parallelizable, then the whole thing would be. For the n log n constructions, you need to compute the effective resistances of the edges, which is like something you can do by solving systems of linear equations. So I think solving systems of linear equations is parallelizable, so you can get these probabilities, and then the sampling is very easy to parallelize. So I think n log n definitely parallelizable. Order of n would have to look into the details of the algorithm of Lee and Sun.
Thanks.
Sure.
Okay, thanks. Are there more questions?
Sorry, so I have one little question. So concerning your problem with hypergraphs, I mean, even for the complete graph, meaning the construction of expander hypergraph, is there something known which like where you have like little O of n log n bounds? Or?
Yeah, the thing is, for hypergraphs, there are a number of competing definitions of what would it mean for an expander to be for an hypergraph to be an expander. So in particular, the most popular notion is that of so-called high-dimensional expanders, and those have different properties. So they wouldn't sparsify a complete hypergraph. However, I think that it is possible to get a sparsifier of the complete hypergraph with order of n hyperedges by, although this is not a well investigated notion, so I'm not sure if what I'm saying now is actually correct, by looking at random walks in an expander. So you could construct so say you want to approximate the hypergraph that contains all hyperedges of size k. I think you could do that by looking at length k random walks in an expander graph, and that this sort of would come in and out of all sets of a certain size roughly with the right probability because of Chernow bounds on expander walks. But I don't, this is being recorded, I don't 100% guarantee that this works, but I think it should work.
Yeah, thank you.
Thank you. Anybody else?
For this hypergraph problem in general, if you loosen the requirement that you want to approximate only some fraction of the cuts, would it be easier?
I don't know. Like to, do you think in terms of a data structure or in terms of
existential?
Just existential.
Mm-hmm.
Yeah, I think in that case, it might be enough to sample order of n hyperedges, because then and then weigh them appropriately. Because now every cut has a good probability of being preserved from Chernow bounds, and then that means that most cuts will be preserved.
But as you said, even in the graph case, even the points, even point cuts kind of.
That's true, but so that depends what you mean by most, because there are 2 to the n cuts, and those are only n of them. Mm-hmm, if you wanted a randomized construction where every cut has a high probability of being preserved, then that gets trickier. I couldn't answer the question of the top of my mind.
Mm-hmm. Yeah, thank you. Mm-hmm.
I actually have a question about these lower bounds that you're using. If they have some relation with the thin trees that were used by in the ATSP paper by Gumans and others, because it looks like you're preserving cuts in a kind of random spanning tree. So I just was wondering if somebody has looked at that.
Right, so the so in the thin trees you have like this is
I'm sorry, I didn't mean to put you on the spot there. So.
No, because sort of so there your graph is a spanning tree where you're not allowed to weigh the edges. It just has to be a spanning tree. And then you have the stronger condition that your graph is k-connected. And then you're asking things like, can I find a spanning tree that, so that every cut in the spanning tree is like a 1 over k fraction of the corresponding cut in the original graph. So if instead of having an assumption of k connectivity, you have an assumption on the effective resistance, then there is something that you can get not from Batson-Spillmann and Srivastava, but sort of. And so the question for thin trees is sort of, you have something weaker because it's combinatorial instead of linear-algebraic, and also get the consequence that is weaker. Now the lower bounds that we have, so the lower bounds that are saying that what's happening in Batson-Spillmann and Srivastava, it's about right. What is the strongest possible conjecture that has been made for thin trees? It's that some kind of combinatorial analog of Batson-Spillmann and Srivastava is true. So our lower bound would not refute any of those conjectures, it would just be some other way of saying that this is a kind of the most you can hope to conjecture. So, there is a relation between these kind of questions, but specifically the lower bounds that we have don't say anything useful, or sort of are not going to refute any of the conjectures that have been made there.
Okay, thanks. Is there any more questions?
I have one question. Okay.
Yes, go ahead, Thiago.
In the case of hypergraphs, do we have a better results if the number of vertices in hyperedge is a fixed number?
If it's a fixed number?
Yes.
No. In fact, the bounds were every hyperedge is at most k vertices are the same as if each hyperedge is exactly k vertices.
Mm-hmm.
Somehow having smaller hyperedges, at least for the known ideas, it's only making things easier. It's not making things harder.
Mm-hmm. Thanks.
Sure.
Anything else?
I have a question.
Yes, please go
you
ahead.
mentioned the connection. You mentioned the connection to random walk. So I was just wondering, at least in the graph and maybe similar in the hypergraph, if you can sample the edges for the sparsification, let's say by take a random walk until cover time, which at least in a complete graph, it's order of n log n. If that will be, and picking those edges, will that be similar to the sparsification result?
Yeah, it's actually an interesting question. Like at some point with several people, we presented a grant proposal to the Simons Foundation that had something to do with some of these ideas, among others. And then we went to New York to give a presentation, and Jim Simons was there and asked exactly your question when we were talking about sparsification. So the thing is, it wouldn't, like, maybe there is something that can be done interestingly with random walks, but it wouldn't give you a sparsifier for general graphs. And I think a good kind of example to look at, it's the dumbbell graph, where you have to pick that edge in the middle, and you have to give it weight that is different from the others. So first of all, like n log n random walks would not discover that edge if you have like n square edges per side. That's very low probability. And also you have to give that edge in the middle a different weight. So something your technique must be able to tell you things about different edges having to have a different weight. However, there are graphs different from this one in which it is possible to give all the edges the same weight. And for those graphs, that might be cleaner or easier way to so do the edge selection. In particular, like the reason, so it could be that you could get n log n by something that it's more like random walks. By the way, something that we don't know about this setup, we don't know an algorithm that, given a graph for which a sparsifier with constant times n edges exist, in which all the weights are the same, to find a sparsifier with order of n edges in which all the edge weights are the same. In fact, even something that doesn't work always, but works under certain sufficient conditions, we don't know. And in fact, here it's the simplest example where we don't know anything. The hypercube can be sparsified with using constant times n edges, n over epsilon square edges, in such a way that all the edges of the sparsifier have the same weight. We have no idea that's a non-constructive proof. We have no idea what such a sparsifier might possibly look like.
Thank you.
Okay, thank you all for the questions. Luca, thank you again for this very nice talk. So, well, let's, I guess, everybody thank Luca again.